right, well, thank you very much, Joe. I'm honored to be back at Q2B for the 8th year in a row. The theme of Q2B is the road to quantum value. And so I'll start with a slide I showed last year. As best we understand, the road to quantum value will be through fault-tolerant quantum computing. We're in the NISQ era, and NISQ is already valuable for scientific exploration, but there's no proposed application of NISQ computing with commercial value for which quantum advantage has been demonstrated when we compare to the best classical hardware running the best algorithms for solving the same problems. Nor do we have persuasive theoretical arguments indicating that commercially viable applications will be found that do not use quantum error correcting codes and fault-tolerant quantum computing. NISQ is a deliberately vague term. It conveys an idea that we have quantum machines now which we can't by brute force simulate with the most powerful existing conventional computers. But these devices are not error corrected, and noise is a serious limitation on their computational power. We can foresee in the future having FASC technology, fault-tolerant application scale quantum computers, which can run a wide variety of applications, but that may be a ways off. What term should we use for the road along the path from NISQ to FASC? Various suggestions have been made building on the ISQ format of NISQ. I suggest we leave the ISQ behind as we move forward. Today, I'll speak of a Megaquop or a Gigaquop machine, meaning one capable of performing 1 million or 1 billion quantum operations, with the understanding that when I say Megaquop, I mean not precisely 1 million operations, but something in that vicinity. Now, naively, a Megaquop machine would need a logical error rate per gate of about 1 in 1 million, and that's not something we expect to be able to achieve anytime soon without using quantum error correction. It might not have to be quite that good because we'll be able to use error mitigation methods in the Megaquop era, just as we do now in the NISQ era. Importantly, we expect that the Megaquop machine would be able to perform tasks which go beyond what we can do with NISQ, as well as with classical computers or with analog quantum devices. For example, by running circuits with of order 100 logical qubits and with a circuit depth of order 10,000. So what resources will we need for such a machine? That depends on a lot of things, but it's a reasonable expectation that tens of thousands of high-quality qubits would suffice. Now, when will we have a Megaquop machine? I don't know. But if it's going to happen in the next few years, the most likely modality will be Rydberg atoms in optical tweezers. And what are we going to do with it? I don't know. As a scientist, I'm interested in what we might learn about quantum dynamics in the Megaquop regime. Will it have commercial as well as scientific applications? I can't promise you that. Now, as we proceed along the path to quantum error correction, what are we going to need? We'd like to see many repeated rounds of accurate error syndrome measurement in a quantum code, such that when the syndromes are decoded, quantum memory times improve sharply as the code increases in size. We want to be able to do accurate real-time decoding of error syndromes. That'll be needed for universal fault-tolerant quantum computing. And we would like the universal gates to also have much higher fidelity than physical gates, and for those logical gate fidelities to continue to improve sharply as codes increase in size. And we'd like to do all this with some acceptable cost in overhead in both the number of physical qubits and the number of physical gates. And we should remember that speed also matters. We would like the time on the wall clock for running a fault-tolerant quantum computation to be as fast as possible. The current state of the art is captured by recent results from Google Quantum AI. Their recently introduced 105-qubit Willow processor has an improved gate error rate, measurement error rate, and leakage correction compared to its predecessor, Sycamore. With Willow, they can perform millions of rounds of surface code syndrome measurement, each one lasting about a microsecond. And most notably, the logical error rate for quantum memory improves by about a factor of 2 each time the code distance increases by 2 from 3 to 5 and from 5 to 7. That's the factor they call lambda. They performed real-time decoding of the error syndromes for both the distance 3 and distance 5 surface code. And to probe the performance of the machine, they've also studied the repetition code, which can correct only bit flips, up to a much larger distance. What we would like to see looking ahead is a much better value of lambda, larger code, so much lower logical error rates for quantum memory, but also high-fidelity logical 2-qubit gates, which perform much better than the physical gates. I expressed concern last year about the vulnerability of superconducting processors to ionizing radiation, like cosmic ray muons. Those events deposit a lot of energy in the chip, which can cause many qubits to fail at once, overwhelming the power of the quantum code to control the errors. And I suggested we might want to operate a superconducting processor deep underground to suppress the muon flux, or use less efficient codes that can protect against those kind of error bursts. But the good news is, through what they call gap engineering, the Google team has greatly improved the resistance to ionizing radiation of their superconducting qubits. Events that cause error bursts that occurred about once every 10 seconds in Sycamore now occur only about once per hour in Willow. I'm not sure that's enough for us to run very deep circuits on future devices, but it's an important step forward. And incidentally, we don't really understand currently exactly what's causing those error bursts that occur about once an hour, which reminds us that not just with superconducting qubits, but other modalities as well, we're bound to encounter rare events with very deleterious effects, which we'll need to understand and mitigate. As I mentioned, we want to do real-time decoding of error syndromes. We need that for universal quantum computation because during a fault-tolerant computation, we have to frequently measure encoded blocks and then perform subsequent operations conditioned on those measurement outcomes. And if we have to wait a long time for the measurement outcome to be revealed by the decoder, that will slow down the logical clock speed. The Google team performed real-time decoding with a latency at distance 5 of about 60 microseconds. That's the time between when the decoder receives the measurement results and when it returns the decoded outcome. And there's about an additional 10 microseconds of communication time from the measurement results to the workstation that runs the decoder by Ethernet connection. Riverlane and Rigetti have observed in smaller experiments that we can improve the latency using FPGAs instead of CPUs to do the decoding, and reduce the communication time by integrating the FPGAs into the control system of the device. In other decoding news, the Google DeepMind team showed that through reinforcement learning, we can have decoders with logical error rates that are lower compared to decoders designed by humans. It's not clear how well that will scale because the needed training becomes hard as the code distance increases. And another interesting idea in decoding from the Harvard and Quira team is that we can do correlated decoding across multiple blocks that reduces the depth of a fault-tolerant simulation, but it also increases the complexity of decoding. So there are open questions about how that strategy will scale as well. Now, the superconducting qubits in the Google machine, also IBM and other companies and labs that have superconducting processors are transmon qubits. Transmons are the simplest superconducting qubits, and they're bound to continue to improve with advances in fabrication and materials. But a logical qubit is going to be a very complicated object, so you can take the point of view that we can afford to make the physical qubits more complicated if there's some corresponding gain in performance that might make it easier to realize a logical qubit down the road. And there are various versions of this strategy that are pursued. One is cat qubits, where the qubit is encoded in a superposition of coherent states in a microwave resonator. In that case, bit flip errors become exponentially suppressed as the mean photon number in the resonator increases, and the phase errors have a rate that only increases linearly. This year, the AWS team demonstrated that by passively protecting against bit flips and using a repetition code to correct the phase errors, they can see a slight improvement in logical error rate when the repetition code distance increases from 3 to 5. Another important idea is that if we know when and where in a circuit errors occur, then error correction can be more effective. One way of making the errors detectable is using a dual rail architecture. For example, we can encode a qubit in a pair of microwave resonators where there's a single photon in either one resonator or the other, corresponding to the 0 or 1 of the encoded qubit. And the Yale team in QCI has demonstrated that in dual rail qubits, where the dominant errors are loss errors, the loss can be detected without disturbing a coherent superposition of a 0 and a 1, such that over 99% of the loss errors are detected and other errors are suppressed in comparison. And the AWS team reported similar results for a dual rail encoding in a pair of transmons instead of a pair of resonators. Another idea is to use states which are highly squeezed in two complementary quadratures in a microwave resonator to encode a finite dimensional system. And the Yale team this year demonstrated that we can encode a 2, 3, or 4-dimensional system in a resonator using that scheme, where the error rate is lower by a factor of about 1.8 compared to the rate of loss from the resonator. Fluxonium is a more complicated superconducting qubit because it requires a high inductance, and that's achieved with an array of Josephson junctions. But what one gets in return is stronger anharmonicity, which enables quite high fidelity 2-qubit gates with more than 3 nines of fidelity, demonstrated by MIT and Atlantic Quantum. Now, I'm not sure whether any of these strategies for trading simplicity for performance will be the right path to follow, but it's important to pursue currently because it might actually ease the path to very low error rate logical performance. Now, we've also seen improvements in error correction this year with atomic qubits, both in tweezer arrays and in ion traps. In those systems, the atoms are movable, and that makes it possible to perform 2-qubit gates on any pair of qubits, and that enables us to use more efficient coding schemes. And in fact, logical circuits have been performed with atomic qubits. The Harvard-MIT Quera team sampled circuits with 48 logical qubits in a 280-qubit device. That was the big news at last year's Q2B. Atom Computing and Microsoft have executed a circuit with 28 logical qubits in a 256-qubit device. Quantinuum and Microsoft, using an ion trap, have prepared entangled states of 12 logical qubits on a 56-qubit device, and I understand they announced some improved results yesterday. In all these cases, though, just a few rounds of syndrome measurement have been performed, and the circuit simulations rely on post-selection, that is, one discards the runs of the circuit in which errors are detected, and that's not a scalable scheme. Efforts to address that drawback are in progress. And also, while the movement of the atoms enables us to perform 2-qubit gates, not restricted by geometric locality, the movement can be quite slow, which slows down the logical clock speed. So if we want to use these platforms to run very deep circuits in the future, it'll be highly desirable to speed up the movement by quite a lot. So how can we progress towards a Megaquop machine? Using high-rate codes like those recently developed by IBM can be helpful. Those codes require non-local connectivity, so at least for now, they're better suited for atomic platforms than superconducting platforms. Using error mitigation methods that are tailored for logical circuits could also be helpful, as is being developed by Kedma. The Google team recently came up with a scheme for improving the overhead cost of doing universal fault-tolerant quantum computing in surface codes, which can also be applied to other codes, and that will help too. What kinds of applications will we run? Well, probably we won't be able to run interesting chemistry applications, since those typically require circuits of quite high depth. A more tempting application would be to materials, where we can take advantage of symmetries and various circuit optimizations, like Phasecraft has been pushing, to potentially bring informative studies of materials within the reach of a machine at the Megaquop scale or somewhat beyond. Scientifically, it'll be interesting to use Megaquop machines to study quantum dynamics in a regime we haven't had access to before. When thinking about quantum advantage, of course, we should always bear in mind that the competing classical algorithms are also developing rapidly, including a lot of improvement in the past year in classical algorithms for simulation of quantum dynamics. So, to summarize, it seems that advances in hardware, control, algorithms, error correction, error mitigation, and so on, are bringing us closer to a machine at the Megaquop scale, which raises a compelling question for our community. What are the potential uses of a Megaquop machine? Progress will hinge on innovation at all levels of the stack, and our applications development will be informed by the capabilities of early fault-tolerant machines, and in turn, our ideas about applications will guide the advance in the technology. We need progress in both the basic science and systems engineering to move ahead. We're still in the early days of quantum computing technology, but I expect that what we can learn from a Megaquop machine will guide the path to gigaquops, teraquops, and widely impactful quantum computing that'll benefit the world. Thanks for listening.
Thanks, John. Okay, so we have time for one question. We're going to take one question now, and then as a reminder, tomorrow we have an Ask Me Anything where we'll get to a bunch more questions.
Right.
So the one for you right now, can you comment on how higher education, teaching, not just research, should catch up with the development of quantum computing?
Well, I mean, I have a point of view about this which may differ from that of people in the companies, I'm not sure, because I am a university professor, and I really think that the quantum companies will benefit a lot from a workforce that has experience with research, that is familiar with attacking hard problems and solving them. So I don't really think what we do in the universities needs to be that much different. I think, at least at a place like Caltech, our priority will be to train people who understand how to address and make progress on really hard problems in quantum science.
Great. All right, thank you, John. Everybody give John a warm welcome here. Thank you so much, sir.
Okay.
All right.